Hello all, my name is Arnab Fani. In this talk, I'm going to present our paper, Uplift Parallelization Strategies for Feature Transformations in Machine Learning Workloads. Feature transformation is a part of feature engineering that scales, modifies, or converts features into numeric representations. Feature transformations are typically placed after data cleaning and before or within the training pipelines. Commonly applied feature transformation includes numerical transformations such as aggregation, scaling, and binning. Common categorical feature encoding techniques are recoding, dummy coding, and feature hashing. Dummy coding is also known as one-hot encoding. Furthermore, modern ML systems provide high-level utilities for encoding data modalities like texts and images. Two common transformations for texts are bag of words and embeddings. Feature transformations are typically applied in two phases. A build phase first obtains the necessary metadata, and an apply phase uses the metadata to transform the input feature. Major challenges of feature transformations include many distinct items per column. For example, a publicly available Criteo dataset has a few columns which have more than 70 million distinct items. Previous work reported similar numbers in their production pipelines. Moreover, the number of distinct items vary drastically across columns. In the same Criteo dataset, some features have less than 10 distinct items. A big part of categorical feature encoding is expensive string processing, such as hashing and sparsing. One-hot encodings typically produce ultra-sparse large output with millions of columns. And finally, data scientists need to apply different combinations of feature transformations to find the best performing combination in terms of accuracy. Existing approaches use techniques to solve these problems like reuse of redundant feature transformations, row and column-wise static parallelism, and interleaving element-wise transformations with data loading. These approaches yield good runtime for simple transformations, but fail to improve complex multipass transformations with large dictionaries. To address these challenges, we introduce Uplift framework. Uplift aims to exploit available parallelism by constructing a fine-grained task dependency graph. We then pass this task dependency graph through a rule-based optimizer that rewrites the task graph according to data, hardware, and operation characteristics. Finally, we submit the task graph to a cache-conscious runtime for concurrent execution. Furthermore, to foster future research on feature transformation, we propose the FTBench benchmark with transformations and datasets from various domains. We also provide multiple full and partial implementations for the benchmark. We integrated Uplift in Apache systemds as a reference ML system. We first describe the system architecture of Uplift. Uplift reads the transformation specifications via a JSON file and creates general and encoder-specific tasks. As an example, we will see the transformations of the adult dataset. We perform binning for numerical and recoding for categorical features, both followed by dummy coding. First, we schedule the parallel binning and recoding build tasks. A build task scans an assigned feature and creates the necessary metadata, such as a dictionary of distinct items and bin boundaries. Once the dictionaries are built, we pre-allocate the output matrix. This upfront allocation allows the apply tasks to concurrently fill the output matrix. We determine the upper bound of number of non-zeros in the output and accordingly allocate a sparse or dense matrix. For a CSR sparse matrix, we already fill the row pointers during the allocation to avoid shifting during concurrent apply. Systemds materializes the consolidated metadata in a frame. A metadata allocation task pre-allocates this frame. After allocations, we schedule the feature-wise binning and recode apply tasks. These tasks encode the assigned features using the metadata and produce integer domains. Then the dummy code apply tasks transform the integer domains into sparse vectors. Finally, we schedule a sparse row compaction tasks to remove zeros from the sparse rows. Zeros may appear while encoding missing values, and the metadata collection tasks materialize the metadata to the pre-allocated frame. After construction, we pass the task graph through an optimizer. Our rewrites aim to minimize compute time under a given memory constraint. We first scan the task graph to remove unnecessary synchronization points. In this example, we perform binning on one column and feature hashing on another column, both followed by dummy coding. In this case, though, even prior to the build tasks, we can derive the output dimensions from the number of bins and the feature hash domain. This allows us to remove the dependency between build and apply tasks. The rest of the dependencies change accordingly. Column-oriented task partitioning fails to fully utilize all the cores if the input has fewer features than available cores and if the compute time is skewed across columns due to varying number of distinct items. To exploit available parallelism better, we additionally partition a column into multiple row ranges and assign a task to each block of rows. In this example, we partition each build task into two partial build tasks and schedule a new merge task to merge the private dictionaries. Similarly, we partition each apply task into two. We utilize the same sample-based memory estimator, which estimates the memory overhead of the partial maps from the estimated number of distinct items and average string sizes. We observe that the increasing number of partitions increases memory overhead. Heuristically, we schedule more tasks than cores to mitigate skew. Our optimizer then tunes the number of partitions based on the memory estimates. In this example, we schedule a single record build task per feature because the estimated total size of the partial maps exceeds memory constraint. As a basis of our evaluation and to foster research on feature transformation, we define the FTBench benchmark. FTBench leverages publicly available datasets from UCI, Kaggle, and A-Miner. We augment the benchmark with synthetic datasets to capture choke points reported by earlier work. Use cases of FTBench includes various domains and modalities such as numerical, categorical, text, and time series, different data and transformation characteristics, varying number of distinct items, large number of distinct items, number of bins, varying string lengths and sparsity, different workload types such as batch and mini batch. We also provide scale factor for a selected use case to control the input sizes. In this slide, we see all the 15 use cases at a glance, covering transformations such as binning, dummy coding, scaling, count vectorizer, and embedding on text dataset, and an end-to-end feature engineering use case. A few examples of scaled use cases include large number of distinct items producing ultra-sparse output with 6 million columns, a large number of bins, bag of words with many distinct tokens, and varying string lengths up to 500 characters. In this section, we discuss a few micro benchmarks and a subset of FTBench use cases. We provide two full implementations of FTBench, one for UPLIFT and systemds and another for scikit-learn. Moreover, we provide partial implementations for Spark, ML, TensorFlow, Keras, and Dask. In this micro benchmark, we measure the speedup with increasing number of threads. The figure shows recode improves up to 10x at 16 physical cores. Despite producing an ultra-sparse output with 10 million columns, dummy coding performs equally well due to efficient sparsity handling. In contrast, feature hashing shows a smaller speedup because it is a memory bandwidth bound operation. In this micro benchmark, we study the impact of number of partitions for build and apply tasks. We systematically increase the number of build and apply partitions from 1 and 2 to 128 and 256. The figure shows the performance improves up to 8 and 16 partitions. Beyond that, the overhead of the partial maps and their merging increases. Feature hashing is robust to task provisioning as it has no metadata. Note that our optimizer also picks 8 and 16 partitions for this dataset. Now we will see the results of FTBench use cases. This figure shows the runtime of all the baselines for the use case T1, which is on the adult dataset. The observations are systemds and scikit-learn are 32x and 52x faster than Keras. UPLIFT further improves by 6x. Dask and Spark static parallelization schemes are ineffective for smaller datasets, while UPLIFT is nearly 10x faster than Spark ML. Here we see the runtime for a subset of use cases on structured datasets. UPLIFT is consistently faster than systemds and scikit-learn. Spark's row-based parallelism continues to be ineffective for smaller datasets such as KDD. However, Spark improves over scikit-learn by 2.5x for larger dataset Criteo, although UPLIFT is 3x faster than Spark on Criteo. These results show UPLIFT's dynamic parallelization schemes significantly improve across various data and transformation characteristics. Finally, we evaluate the use cases reported by the earlier work. First, we systematically vary the string lengths from 50 to 500. UPLIFT is consistently faster. However, the speedup drops with increasing number of characters due to more cache misses. Second, we vary the number of distinct items from 100K to 1 million per column. We see increasing speedup up to 30x and 11x for scikit-learn and systemds respectively due to multi-threaded latency hiding. To summarize, we introduced UPLIFT framework to parallelize feature transformations with fine-grained task scheduling, and FTBench benchmark to evaluate such frameworks on a variety of transformation workloads. We also made the reference implementations publicly available. Feature transformations are an incredibly common part of ML development. With increasing multimodalities, transformations are becoming more and more challenging. We showed that UPLIFT's parallelization strategies can tackle varying transformations. Interesting future work includes extending UPLIFT framework for distributed data parallel operations and federated backends, a cost-based optimizer, scan sharing, and with techniques such as scan sharing and fusion among transformations. Finally, FTBench can be improved by additional reference implementations for more baseline ML systems. Thank you.